Hi everyone, this is Janine aka Janine the Tutor. As you know, now is a very difficult time for each one of us, whether you're in middle school, high school, or university. Many students and families are deeply affected by the recent school closure. And as a part of OneClass, we are very fortunate that we are able to adapt to the circumstance quickly, and that's why we want to help you stay on top of your studies by running free and daily classes for math and chemistry from grades 11 to first year college and university. So for today's class, I will be going over calculus and vectors. And before we get into today's class, I just wanted to ask you if you know anyone, any of your friends who might be interested in staying productive and on top of your studies, please invite them and ask them to join. Okay, great. So let's begin. Just wanted to make sure if you guys can see my screen and also if you can hear me coming through. Okay, so this is where we left off. So we were trying to fill out the sign chart. So again, the sign chart is really helpful in terms of trying to see where your inflection point is, where your cusp or corners are, if there are, and also your concavity, right? So your second derivative tells you whether your function has concavity, right? So in that case, if we're looking at, okay, so we filled the first derivative and the second derivative. So just as a recap, basically all you have to do is plug in any number that is, for example, within this interval. So any number that is less than -7, any number that is between -7 and -14/3, and also any number that is in between -14/3 and 0. And also finally, any number that is after 0 or greater than 0. And all you have to do, if you're looking at the first derivative, that means you have to plug in that number and see what the sign is for that first derivative. And also for the second derivative, you're supposed to do the exact same thing, right? Pick any number in that interval, and then you have to plug that in as your x and see what happens to the sign of your second derivative. Great, so now we've accomplished that. Now we look at our function, right? So in our function, if you have a positive for first derivative and also a positive sign for the second derivative, that means your function is increasing and your function is also concaving up, right? That's what it means. Now, if you're looking at your function, if your first derivative is positive and then your second derivative is negative, that means you're concaving down, right, for your second derivative, but your function is increasing. That's why it's still going upwards, right? And then if you have this being both negative, right, that means your function is decreasing and also your function is concaving down, right? So for your function to be decreasing, that means your arrow needs to go downwards. And on top of that, for it to be concaving down, well, it's only going to be this, right? If you have your function decreasing. Then if you have your function, so your function is increasing, but your function is concaving down, right? So if it's increasing, that means your function needs to go upwards and your function is concaving down, so that would be this, right? Okay, so this is how your function looks like. Now, if we were to identify where are your points of inflection, where are your local max, and if it's applicable, if you do have a local min, right? If you do have any corners, you have any cusp, right? So maybe we can identify that. So we were mentioning from previous class that our critical values are basically at x is equal to -7, you have -14/3, and you have 0, right? And okay, so we didn't really go over that. So if you notice, you have your local max at -14/3 right here. So let's say, how do you find what the y value is, right? And how do I know? I do have a local max at -14/3. Okay, so if you check this over here, so here you have -14/3, and here you have, let's see. Okay, so this is where -14/3 is, right? So you have something like this. So as you can see, this over here, if you try to connect the two, like f of x, right? The direction of where your function is going, right? If you connected this and then you have this, right? So this is going upwards and basically you're going down, right? And then before you change concavity, okay, so it's something like this. So that means at x is equal to negative 14 over 3, you know that there's a local max, right? So we can say that because it's going up from negative 7 to negative 14 over 3, and then basically at negative 14 over 3, you do have a local max, which is also a turning point. And then from there, from negative 14 over 3, comma 0, you basically concave down, and then you do have a cusp, right? You do have a corner. So it's a sharp corner where you change your sign. Okay, so we can say that you have a local max at negative 14 over 3. But here's the thing, how do I know what the y coordinate is, right? What's the corresponding y value in my function when I do have a local max at negative 14 over 3? So all you have to do is take negative 14 over 3 and plug that into your function, right? So you don't plug negative 14 over 3 in your first derivative or second derivative, right? Because the whole point of having negative 14 over 3, if you look at our previous function over here, we said that if you have your first derivative being equal to 0, you're going to get a critical value, which is x is equal to negative 14 over 3. And if you do plug negative 14 over 3 back into your first derivative, right, you're just going to get 0. So that doesn't really answer what the y value is. So you have to take this, right, and plug this into your function, which is this, right? So if you plug in negative 14 over 3, you're going to get 3.7, right? So plug negative 14 over 3 here, you get 3.7. So we can say that you do have a local max at negative 14 over 3 comma 3.7, right? So we can actually mention that here. So local max at negative 14 over 3 comma 3.7, and then let's see if you do have a local minimum, right? So here, as you can see, I mentioned you do have a sharp corner or a cusp, right? Because it's basically going downwards and then you move up again, right? So this is a cusp. Can you guys see this? So as opposed to having a local minimum, you have a local cusp, right? Because if you do have a minimum, right, it has to be a turning point, but this is not a turning point. So in that case, we're going to say that we do have a local cusp when it's 0, right? And how do you find the y value? Remember, you go back to your function, f of x, you plug in 0, and then if you have 0 times any number would give you 0, therefore you do have a local cusp at 0, comma 0. So 0, comma 0. Okay, great. So local cusp, right? Yeah, so this is not a local minimum, so you don't have a local minimum, but you do have a local cusp. So this is 0, comma 0. Great. And let's move on to our point of inflection. Okay, so point of inflection is basically you have a change in concavity, right? So if you notice, right, so all of your sign for the second derivative, starting from here, negative 7 comma negative 14 over 3, until you get to 0 comma infinity, they're all negative, right? So if they're all negative, right, basically the only change that you're seeing right now is when it's at negative infinity to negative 7, right? And negative 7 to negative 14 over 3. So there is a change in concavity, right? You are concaving up here and you are concaving down when you reach this interval, right? So that in that case, you can say that you do have an inflection point over here. So there is an inflection point, right? Because if you connected this and this, you're going to see that yes, you are changing in concavity. Therefore, as a result, you do have an inflection point. So you do have an inflection point at negative 7. So this negative 7 is basically your x, right? And how do you find your y value? Then all you have to do is plug that into your function. So if you plug that into your function, so negative 7 plus 7 raised to the power of 1 over 3 is 0. Therefore, any number, right, you multiply that to x. And if you have negative 7 raised to the power of 2 over 3 here, that would just become 0, right? Because you know that this term would eventually be 0, then you multiply that, you get 0. So in that case, you do have an inflection point at negative 7 comma 0. So point of inflection, IP, is negative 7 comma 0. Okay, great. So once we filled all of our conditions and the things that we're being asked to look for, now we can finally sketch the graph, right? And also, I just wanted to remind everyone that anytime you're curve sketching, so expect that your teacher will actually ask you these questions, and I think they're really helpful to do just because you need them, right? You need these information to graph your function, because otherwise, if you don't have the sign chart, you don't know what the critical values are, then how do you expect yourself to graph your function, right? So even if one of them is missing, right, on the test, just make sure you know how to solve for your x and y intercepts, and also you know how to identify what your points of inflection are, right, if there are multiple, just because it's really helpful when it comes to curve sketching. Okay, so this is your x and y axis. And yeah, so we start by marking where our inflection point is. So you have negative 7, and this is basically at 0, right? So you have an inflection point here. You have a local max at negative 14 over 3. So negative 14 over 3, just for your reference, is... This is about negative 4.7, just so we know. Yeah, personally, I'm just conditioned to convert improper fractions into decimal numbers just so it's easier to see. Okay, so this is negative 4.7, so that's somewhere here, right? Negative 14 over 3. And then basically you have a local max, so that means it must be a peak. So it's somewhere here, and this is basically 3.7. Okay, so we have a local max here, and we do have a cusp here, right? And let's find our x-intercepts and y-intercepts based from earlier. So you do have an x-intercept at negative 7 comma 0, and this is what you know your inflection point. And you have 0 comma 0, so that's where your cusp is, and also your y-intercept is at 0 comma 0. You don't have any asymptotes, so you don't have to worry about your asymptotes. And you're seeing that your function has a domain, all real numbers, right? And range is also all real numbers. So we're ready to graph our function. So you have an inflection point. Inflection point just means you have a change in concavity. So initially you are concaving up, right? So here, concaving up, and you hit this point. Okay, great. Now concaving up, now you're concaving down. Okay, this is not... Okay, let's make this smoother. Okay, great. So this is an inflection point at negative 7 comma 0. Then you have a local max, right? So there is a turning point, and this is concaving down, right? So once you've concaved down, right, there is a local cusp. There is a sharp turn or corner over here, right? So you have a cusp here, and that you can see, right? Because in a local cusp, your horizontal tangent is not 0, right? That's the difference between a local max, local min, and a cusp, is your slope, right? Sorry, did I just say horizontal tangent? No. So I'm referring to the slope, right? So if you're looking at your local max or your local min, the reason why it's called a turning point, it's because your slope here, your horizontal sorry, not horizontal, but your slope here, horizontal line rather, not horizontal tangent. If I did mention that, let me correct myself. So your horizontal line is basically 0, right? The slope here is 0. That's why it's flat, right? So that's the difference between a cusp and your local extremas. Because if you look at your local max and min, that differs, right? Having a slope of 0 differs from a cusp, because in a cusp, you don't have a slope, right? Okay, great. So we finished curve sketching, and I think that's about it. And make sure that this extends all the way until negative infinity, right? Until you get to negative 7. Okay, so I think we can move on to today's class now. Okay, let me just find the sheet. Okay, great. So hopefully you guys can see this, and we're now going to do some, yeah, this is like vectors. I would say this is, so this is a question that has something to do with vectors now. Okay, so as you can see, we have a time, right? At 11:22 a.m. on a Sunday morning, John was at an intersection in his car. Okay, so there's going to be a lot of information, so we need to start underlining things. And the question says he was at 67 kilometers due north of Mike, who was also in his car. Okay, so there's two people. So we have John and Mike. So maybe John is here and Mike is over here because Mike is going north, right? So he was at 67-kilometer due north of Mike, who was also in his car. Great. So 67 kilometer. Okay, so this is supposed to be a straight line, okay, because it's north, right? It's not northeast or okay, great. So this is the distance, and it says John was traveling west at a speed of 52 km per hour. Okay, so going west is this way, right? So Mike, we're assuming that he's going north. And it says, meanwhile, Mike was going north at 102 km per hour. Okay, here's the thing with vectors, right? You cannot combine the information when they're trying to give you speed or velocity in this case because we're dealing with vectors. So there is a difference between the information of having just the distance and also when you have velocity or speed, right? So first of all, you cannot say that 67 is the same as 102 because this is basically the velocity that Mike is traveling north, right? So you cannot share that same information in just one triangle, I would say, or vector. So here it says how close to each other do the two vehicles get and at what time in the day, in hours and minutes, does this occur, right? So essentially we're at this point. So maybe we can call this point B and this being point A. Okay, it's supposed to close, right? So from, oh my goodness, from this point to this point. Okay, great. So from this point to this point. So this is point A. Okay, so we do have 52 km per hour. So that's west, and we have 102 km per hour. This is heading north, right? So Mike heading north. So let M be Mike, J be John, and I think that's it. And then make sure that we know that the time that they started is 11:22 a.m. So first of all, let's just remind ourselves if we have distance, that means it's speed times time, right? So this is your distance equation. And now if you look at your speed in this case, so this is 102. So this is without the vectors, right? Because we know that speed is not a vector. So let's keep 102 km per hour and 52 km per hour as speed. So for you to set up your equation, right, you know that you have to multiply 52 times the time, right? Because here, right, we do have 67 kilometers, right, to begin with, where Mike was initially originating from. So if you have 67, that means when you set up this equation, so when I say AJ, I'm referring to this line segment, right, from this destination until where John is currently, right? So that's AJ. So essentially, we're just solving for the distance, right? So when you set up that equation, that would be AJ, and that's equal to John's distance, right? So they're telling us that it's 52 km per hour. So for you to just have the distance, which is in kilometers, you have to multiply 52 times t, right? Why does it have to be multiplied to t? Well, you want to get rid of your hours, right, in your denominator. So that's why we're doing that. And then for Mike, in this case, let's call this BJ, right? So initially you do have the 67 over here. So this would be BJ. So this is the distance for Mike. So if you have 67 kilometers, therefore you're going to have 67 over here. And then you're going to subtract this from 102, right? So 102 is basically your speed, right? Which is from here to this point, right? That's why you're subtracting. And then because you wanted to just have kilometers, right? You want to get rid of hours, therefore this is times t. Great, so we have this, right? So when we set up our distance equation, right? All we have to do is we take the square root, right? So square root of AJ, right? So we square this, and then we have BJ squared. Yeah, if you guys recall, this is basically the distance equation. If you go back to grade 10, right, you do have your distance equation. So this is the square root of AJ squared plus BJ squared, and that's basically your distance. Okay, so once we have that, maybe we can set up our equation. So let me scroll this down. Okay, so because I know we're not going to have enough space, right? So we can transfer this to another sheet. So let's copy everything that we're seeing. Okay, I guess it doesn't copy the question. Give me 1 second. Actually, let's just continue on with the square root of AJ and plus BJ. Okay, so distance is basically square root of AJ squared, and this is plus BJ squared. Okay, so as I was saying, all we have to do is plug in AJ. So going back to this, we're saying AJ is 52t from here. So this is square root of 52t, then you square that, then you have BJ. So BJ is 67 minus 102t. And then you square this, right? So as you can see, all we have to do is expand this. So if you have 52, you square that. That would give you 2,704. So this is 2704, and this is t squared. So this is when I expanded that. And then you have plus. So just keep in mind that because this is b minus a, right? Then you have squared, right? So applying the formula to this, you would have 67 squared. So 67 squared is 4,489. And because this is plus, that means I can just remove my brackets because I'm not really distributing any negative signs. So everything is just going to be positive, right? So I square this. I multiply 2, right? Times this and this. So 2 times 67 times 102 will give me 13,668. And because I know that this is negative over here, this would be minus 13,668, and this is t, right? So it's 2ab if you guys remember. And then if you have 102t, then you just square this, right? So 102 squared is equal to 10,404. So this is now positive, right? 10,404, and this is t squared. Okay, so once we have that, right, as you can see, we can simplify this and this because these two are like terms. So if you have 10,404 plus 2,704, you're going to get 13,108. Okay, great. So we take the square root of 13,108, and this is t squared, and I don't think we can combine any like terms, so I'm just going to arrange this in a squared or t squared minus t, and then you have the constant. So this is minus 13,668t, and this is plus 4,489. Okay, let's see. I think that's it for this equation. Okay, so now that we have that, right, because they're asking us how close to each other do the two vehicles get, and at what time of day in hours and minutes. Okay, so there's two questions in just this one statement that they're asking for. So it's basically the distance and how close to each other do the two vehicles get, and at, yeah, so it's the distance and also at what specific time in hours and minutes. So that's the question that they're asking us essentially. So if you do have your distance, right, how do you find time, right? That's the question. So also, just remember that for this question, you do need to find the first derivative of your distance, right? Because you want to know the best time that they're going to meet each other. So that's why you need to take the first derivative of d and find t from that, right? So because everything is so everything is in a root. Therefore, we can just say that this is 13,108 t squared, and this is minus 13,668 t, and this is plus 4,489. So what I'm gonna do is I'm going to, instead of having that root, I will say that this is raised to the power of 1/2, right? Because it's just easier for you to take the first derivative, right? And because I wanted to find the best time, right? Or yeah, because we're optimizing in this question, right? So if you have to look for the time, right, where they're going to meet, that means your first derivative, right, for your distance need to be 0. So in that case, I'm taking the first derivative and I'm saying, okay, so I do have this chain rule that I need to apply. I'm taking 1/2, right? And I'm copying my inner term, so 13,108 t squared minus 13,668 t. Then you have plus 4,489, right? And subsequently, I'm going to multiply this with the derivative of my inner term, so 13,108 times 2, right? So how do you find that? You apply the power rule. So your exponent, you bring that down, you multiply that to your coefficient. So that's 13,108 times 2. So that's 26,216. 216, and this is basically t, right? And what else? Let's put this in a bracket just because it's addition. Okay. Now this is just going to be minus 13,668, right? And this is 0. The derivative of a constant is 0. Okay, great. So we have that. Now what happens to, let's see. Oh, and also just keep in mind that once you brought down 1/2, right, make sure that you subtract this with 1, so you get negative 1/2 over here. So when you do rearrange this, you're going to have 26,216 t minus 13,668. Let me just move this. Okay, great. So yeah, just keep in mind that you still do have this. So 13,668, and this is going to be over 2, and remember you do have a root here, right? You do have a square root, so you're going to have that square root back. This is 13,108 t squared. This is minus 13,668 t, and this is basically plus 4,489. Right? And remember, because we're optimizing, you need to equate this to 0, right? So after equating that to 0, you're going to see that when you cross multiply this denominator with 0, you're going to get 0. So eventually you're going to get 26,216 t minus 13,668 is equal to 0. Then you're just isolating and solving for t. So 26,216 t is equal to 13,668, dividing both sides with 26,216. Let's see what we're going to get. So t is equal to, okay, so 13,668. So I'm just going to punch this into my number, sorry, in my calculator, divided by 26,216. Okay, great. So punch this into your calculator. So take t equal to 13,668 divided by 26,216. So this is equal to 3,417 over 6,554. Okay, so remember, because we were dealing with kilometer per hour, so now you know that t must be in hours, right? So once you have this in hours, well, you need to convert the remaining in terms of minutes, right? So in that case, because this is in hours, I'm just going to do a quick unit analysis or dimensional analysis. So you have 3,417 and this is 6,554, and you know that hours is in your numerator, right? So converting this to minutes, I know that for every 1 hour, this is 60 minutes. So yeah, all I have to do is multiply this term with 60 and I should be getting this in terms of hours and minutes as well. So 3417 divided by 6554, you multiply this to 60. So yeah, you should be getting 31.3. And this is in terms of minutes now, right? So because we know that this is in, let's see. Yeah, so this was in hours. You're now just fully in terms of units, it's just minutes, right? So it's basically converting what you have as a fraction, because you know that you're starting with hours, you need to convert to minutes. And why do you need to convert to minutes? Because that's the only way you can change this 11:22 a.m. If you go back to this question, it's basically you're starting at 11:22 a.m. and you wanted to know the time that they're meeting, right? So you're going to add 31.3 minutes to 11:22 a.m., right? So if you added this amount, which is 31.3 minutes, right, to 11:22. So if you started at 11:22 a.m., right? So 22 plus, let's say, 31, right? So we're going to just round this up to 31. So if you added 31 minutes, that would be 11 still, right? And that's basically 53 a.m., right? 11:53 a.m. So that's the time that they're going to meet, right? So does that make sense? So there is a little bit of optimization where you're taking the first derivative, which is in terms of distance, equate that to 0, and then you find the time, right? So once you found the time, basically you're adding that to the time, right, that they started, which was 11:22, and then now we look for the distance, right? So because you know that it's 31.3 minutes, right, how do you find the distance? So the distance, we know that this is in hours, right? And our equation, this over here, so you have 52t squared and you have plus 67 minus 102t squared, and you're taking the square root of that. This is in hours, right? So you don't want to use the 31.3 minutes because that's in minutes. So maybe I can just copy this and okay, so to find the distance that that they're going to meet essentially, right? Because they're asking us how close to each other. So in that case, if you're looking for the distance, you need to use this in terms of, sorry, you need to express your time in terms of hours, right? So maybe what I can do from 31.3 minutes, I don't really need to convert this to hours. I can just even use this one. So let's say you do have square root of 52, then you multiply this to the fraction, which is 3417 divided by 6554, right? Because that's in hours. Then you square this, then this is plus 67 minus 102. You just multiply this to 3417 over 6554. Then you square the whole thing, right? Okay, let's see. So for this, you should be getting, okay, let's try this. So 52 multiplied to the fraction 3417 divided by 6554. Just make sure you do have the brackets to square your term. Then you have plus 67 minus 102 times 3417 divided by 6554. Then close bracket, and then you close bracket again, then you square. So yeah, you're going to see that this is now, okay, I think it's just easier because some people, you're using a decimal calculator, so maybe if we turn this into a decimal number. Okay, just so you know, 3417 divided by 6554 is 0.52. So maybe it's easier to punch in as opposed to having fractions, but this is fine as well, right? You can use fractions, it's really your preference. So if you have 52 and yeah, so this in decimal, if you type this into your calculator because I think it's just easier. If you have 0.52, that's also in hours, right? So this is the decimal version of this. So I'm just rounding this to two decimal places. So if you plug 0.52 here, that should work too. And this is 67 minus 102 t. This is also 0.52, right? So yeah, if you plug in 0.52, let's see what we're supposed to get. So 52 times 0.52, you square that, then this is plus 67 minus 102 times 0.52, close bracket, then you square that. So yeah, you're going to get 30.4 kilometers, right? So this is how close they can meet, and this is the time that you're going to meet, which is 11:53 a.m. Okay, yeah, so for your time, you don't have to convert it to decimal. I'm just saying that it's easier for some students just because they do have a decimal calculator, right? So if you don't have that fraction option, it's going to be harder for you. So it's up to you. You don't have to convert it into decimal. So here are your answers. So it's basically at 11:53 a.m. and they're going to be 30.4 kilometers close to each other for John and Mike. Okay, so I guess that answers the question. And now let's move on to finding the derivatives, right, if you have y and x simultaneously. So I think this is something that not a lot of students tackle in the grade 12 level. Sometimes they even, like you guys even learn this in university or college. So just make sure that depending on your teacher, right, if you're taking an AP calculus class, you might even cover this. So just as a recap, now we're going into derivatives, right, when we're looking at two variables, not just x. Okay, so it's still going to be the same concept that's applied. So anytime you have a 4, right, you apply the chain rule. But now it's going to be a little bit different. So here, if you have x plus y raised to the power of 4 is equal to 23x, right? When they say you're looking for dy over dx, that means you're looking at the first derivative with respect to y, right? So if you have dy over dx, basically all you have to do is bring down your 4, apply the chain rule, therefore you're going to have 4, and this is going to be x plus y. It's still going to be the same, right? And then you take 4 minus 1, which is just going to be 3, right? Exactly the same chain rule that we've been using over and over, right? Since we were looking at the single variable x, right? When we were taking the chain rule for that. So this is x plus y and this is cube, right? And remember, once you've applied the chain rule, you need to focus on your inner term, which is x plus y, right? You need to take the derivative of your inner term. So that's what we're going to do. So we're taking the derivative of x, right? So the derivative of x, because it's containing a single exponent, which is just 1, right? That means the derivative of x is just going to be 1, right? Simple as that. Now here, if we look at y, because we're deriving with respect to y and x, right? That means if you're saying that this is just 1, that means this, the derivative of y, technically it's supposed to be 1, but we're going to say that this is dy over dx, right? And that's it. So we close that. And then now that's going to be equal to 23. So as you can see, anytime you're deriving x, right, if this is just 1, that means you're just going to write 1 for x. But if you have y, it gets a little bit more complicated because you need to say that you do have a y, right? But when you're deriving y, it's also affecting x. So that's why it's dy over dx, right? So you're deriving y based on x as well. Okay, so we need to solve for dy over dx, right? So all we have to do, because we're seeing that you have this over here multiplied to 1 plus dy over dx, we can actually get rid of this first by dividing both sides with 4 times x plus y cube. And this is 4 times x plus y cube. So yeah, this is implicit differentiation because we're looking at two variables now. Okay, so this cancels out. And now we're left with 1 plus dy over dx, and that's equal to 23. Then you have over 4 times x plus y, and this is cube, right? So as you guys can see, we can isolate dy over dx by just having this on one side. Then we can say this is 23 over 4 times x plus y, then this is cube, and this is minus 1. And that's it. We're done. Okay, so maybe we can try another question just to see if we really understand this whole concept of implicit differentiation. Okay, so remember this x plus y is similar to having this being in an exponent of 1/2, right? I'm just going to rewrite this, and you have negative 3x, and this is equal to 2. So all we have to do, remember, is apply the chain rule and just basically bring this 1/2 down. So we're going to have 1/2, and this is now x plus y, right? We're taking 1/2 minus 1, similarly to what we've been doing for chain rule. So this is going to be negative 1/2, and then we're going to focus on the inner term. So we see that x is going to be, the derivative of x is just 1, right? The derivative of y is dy over dx. Then we close that. Now for this, we just have negative 3, right? Because the derivative of negative 3x is just going to be negative 3. And the derivative of a constant, right? So this is now equal to 0, right? Because the derivative of 2 is 0. So yeah, all we have to do is rearrange this in a way that we're going to isolate dy over dx. So now we can see that this negative 3 can be first moved to the opposite side of the equation, and we can rearrange this since we have a negative exponent. So this goes into your denominator. So if you have 1 plus dy over dx, right, and this is all over 2, and we know that this is square root of x plus y, and this is equal to 3. So as you can see, you can cross multiply 3 times 2 square root of x plus y, and you can just have 1 plus dy over dx on one side. So that's what we're going to do now. So 1 plus dy over dx is equal to 3 times this whole term in your denominator, right? So because this is a constant, when you multiply a constant to a radical, which has a coefficient of 2, this eventually becomes 6, right? And you just copy the square root, which is square root of x plus y. So solving for dy over dx, we can say that this is equal to 6 square root of x plus y, and this is minus 1. And so we're done. Yeah, that's it. Okay. Great. So for number 3, let's maybe look at this question. So it says the equation 5xy squared minus 4y squared is equal to x raised to the power 4 implicitly defines y as a function of x, right? Use implicit differentiation to determine dy over dx. So interestingly, if you look at this equation, you're going to see that there is a product rule that needs to be applied here because you're multiplying x and y squared now, right? So this is not just adding x plus y, which was what we've been observing and solving for earlier, right? So you need to apply the product rule here. So it gets a little bit tricky, but what I like to do, instead of having to apply the product rule right away, I split this into applying the product rule first, and then I deal with the entire equation. So let's say we focus on this 5xy squared first. Okay, so when I apply the product rule, so if I have 5xy squared to begin with, I'm going to say, okay, so I'm taking, remember from the product rule, I'm taking the derivative of this first, right? And then I'm taking the derivative of this next, right? So all I'm doing is equating this to 5x, right? Take the derivative of that, then you multiply this to y squared, then you add the 2, right? Then you take the derivative of y squared, then you multiply that to 5x. So yeah, it's very similar to what we've been doing. So here, right, if you take the derivative of 5x, that's just going to be 5y squared, right? So 5y squared. Now for here, if you take the derivative of y squared, that means this exponent needs to go down because you're applying the power rule, right? So you're going to have 2y, right? But if you have 2y, right, remember you're taking 2, bringing that down so that you multiply 2 times y. But remember, for your exponent, basically you're subtracting 1, so that's why it becomes y. But we're not yet done because we're saying that we're taking the derivative of this y squared with respect to x, right? That's why it's dy over dx that you need to multiply. So basically, the additional step that you're applying here is if you're saying that you're deriving y squared, that becomes 2y, and as a result of that, you need to make sure that because you're introducing a different variable which is different from x, you need to say that you're deriving this y with respect to x. That's why you need to have that dy over dx every time you're deriving y, right? So that's what happens here, right? Because if you go back to the previous questions we've been doing, right, if you recall, when you're taking the derivative of this y, of this inner term, right, after applying the chain rule and after taking the derivative of x, we're saying that the derivative of y is 1, right? 1 times dy over dx. So after writing 1, we're saying that we're deriving y with respect to x. That's why we do have that dy over dx. And we don't typically write the 1. That's why it's just dy over dx. So that's what we're doing here. And don't forget, we're still multiplying this to 5x. And that's it. So once we've successfully done that, right, so we do have the 5x over here, we go back to this equation, right? So now we know what this is, right? It's basically this, and we just have to plug that in here. So maybe we can write the 4y squared here, and this is x4. Okay, so maybe we can rearrange this. Yeah, we can take out the 5, right? We can factor out the 5. That's the greatest common factor. Then we're going to be left with your inner term, which is, let's see, y squared for your inside term. So this is y squared, and this is going to be plus 2xy. Then you have dy over dx. Okay, great. So you have that, right? So now this is going to go in here, right? Because that's where your 5x y squared was originally positioned. So you're going to have 5, then you multiply this to y squared plus 2xy dy over dx. And obviously you don't have to take the derivative of this because this is done. So all you have to do is take the derivative of this and this. So you're going to have 5, multiply that to y squared plus 2xy dy over dx. Then I'm going to take the derivative of this. So I'm multiplying 4 times 2, right? That becomes 8y. And remember, to cap it off, you have dy over dx because you're deriving y with respect to x. And that's equal to 4x cubed. And that's it. So all we have to do is combine your dy over dx because you do have that in this term and also in this term. So this becomes 5y squared. This is plus 10xy dy over dx. And this is basically minus 8y dy over dx. And this is equal to 4x cubed. So as you can see, you can move the 5 squared to the opposite side. And you can factor out dy over dx. So maybe we can just combine the two. Let me just move this question after so we can just continue on. So this is dy over dx. Over here, this is minus 8y dy over dx. And this is equal to 4x cubed. And I'm moving this 5y squared to the opposite side of my equation. So I'm getting negative 5y squared. So we can isolate dy over dx, right, by factoring that out because it's the greatest common factor. So when you do that, you're going to have dy over dx, then inside you're going to have 10xy minus 8y. And that's equal to 4x cubed minus 5y squared, right? Because you just wanted to have dy over dx, this is all going to be equal to this 4x cubed minus 5y squared divided by 10xy minus 8y. So essentially you can cancel this and you can cancel this. So you get left with 4x cubed minus 5y squared over 10xy minus 8y. So that's your final answer for dy over dx. Okay, now here's the question, right? If you go back to part B, it says write y as an explicit function of x and compute dy over dx directly. So you need to express this dy over dx in terms of just, let's see, in terms of just x, right? So maybe we can do that. Okay, because apparently for part C, so we're just gonna continue on. So here I'm solving for B, and then for C that's going to drag down a bit. So we have more space. Okay, so for B, let me solve for this. Okay, so we said for B, you have this y as an explicit function of x. Okay, so you do have this function, 5xy squared. We can just write that down quickly. And then you have minus 4y squared is equal to x raised to the power of 4. Okay, so our goal here is to solve for y, right? As an explicit function of x. So basically y is equal to an x term, right? So in that case, because you do have two y's here, you can have a greatest common factor, which is y squared, right? So we're going to take out the y squared, and the ones that will be left inside would be 5x minus 4, and that's equal to x raised to the power of 4, and dividing both sides with 5x minus 4. Then you take the square root, remember, because you're just solving for y. And you get to cancel the square root and the square. So essentially you're going to get y is equal to square root of x4 over 5x minus 4. You can still simplify this because you know that this is essentially equal to taking the square root in your numerator and your denominator. So you can say this is square root of 5x minus 4, right? So we know that the square root of x raised to the power of 4 is actually just x squared. So this is x squared, and this is over 5x minus 4. Okay, so once we have that, we can say that y is equal to this, right? So because we found what y is as an explicit function of x, right, we need to find what the derivative of this is, essentially. So what's the derivative of this when you have x squared over square root of 5x minus 4, right? Because here it says compute dy over dx directly, right? So in that case, this dy over dx is the one that we're solving for. So we're taking our y value, right? Because we've rearranged it. So initially we had 5xy squared minus 4y squared is equal to x raised to the power of 4, right? So we take the first derivative of this. Okay, so how do we find the first derivative of this, right? Remember, we're applying the quotient rule. This is nothing new because we're still applying the same quotient rule and we're only dealing with x, right? So here, we take x squared, take the derivative of that multiplied by square root of 5x minus 4 minus take the derivative of square root of 5x minus 4, and then you multiply this to x squared over 5x minus 4, 1/2, then you square that. So because this is 1/2, you need to square this, right? So when you square this, right, 2 times 1/2 becomes 1. So we can just leave it as 1. Okay, so that's it. So now you would have 2x, then this is multiplied to 5x minus 4, then you have minus 1/2, right? Make sure you bring that down. This is 5x minus 4. Then this becomes negative 1/2 times 5x squared, right? This x squared came from this, and if you take your derivative of your inner term, this is just going to be 5. Okay, so once you have that, right, you have 5x minus 4, right? And maybe we can have a greatest common factor that we can take out and simplify. So Yeah, we can simplify this by factoring 5x minus 4 raised to the power of negative 1/2. That's our greatest common factor. So I'm going to take this out, and I'm going to be left with 2x, right? So if you take negative 1/2 out for your 5x minus 4, you should be left with just 5x minus 4, and this is just raised to the power of 1. And then simultaneously, you're going to have negative 5 over 2 x squared, because you've taken out all of your 5x minus 4, and this is just negative 1/2, right? So it becomes 1. So this is going to be over 5x minus 4. So yeah, we can start simplifying this because we know that this is going to be 0.5 when it goes to your denominator. So now this and this will become 3 over 2, right? For your exponent. So you would have 2x, then you have times 5x minus 4 minus 5 over 2 x squared. So because if you move this to your denominator, because this is originally negative 1/2, that becomes positive when it moves to your denominator. So instead of having 5x minus 4 times 5x minus 4 raised to the power of 1/2, you can actually simplify by adding 1 plus 1/2, so that becomes 3 over 2. Because if you're multiplying two terms that are similar, you just add the exponents. So that's why this is 3 over 2. Okay, so once you know that this is 3 over 2, you can expand your numerator, so you can have 10x squared, and this is minus 4 times 2, 8x, right? Minus 5 over 2 x squared. So you can simplify negative 5 over 2 x squared and 10x squared. So this is 5x minus 4, 3 over 2. This is equal to, let's see. So yeah, 10 and minus 5 over 2 should give you 15 over 2. Yeah, 15 over 2. This is 15 over 2. Then you have x squared minus 8x. Then you have 5x minus 4 raised to the power of 3 over 2. And of course, you don't really want to have a fraction in your numerator, so you can actually simplify this, right? By having the 2 in your denominator. And how do I know that I'm supposed to do that? Well, if you have 15 over 2, then you have x squared, and this is minus 8x. So let's say, so this is in your denominator, right? This 2. And you know that your denominator for 8x is just simply going to be 1, right? So when you, what you call, so this is my method. So when you cross multiply, so if you have 15x squared, this should be 15x squared times 1. That gives you 15x squared. And then this is basically 1 times 2. So your denominator must certainly be 2, right? That's why you have the 2, because 2 times 1 is 2. And then you have the negative sign over here. So you have this negative sign, then you multiply 8x times 2, so that's negative 16x, right? So now you know that this term in your numerator must be 15x squared minus 16x over 2, and then you multiply this to 1 over, or actually you do divide this, right? You divide this with 5x minus 4 raised to the power of 3 over 2, right? So you divide, but if you're dividing, remember you take the reciprocal. Therefore, this is just going to be 1 over 5x minus 4 raised to the power of 3 over 2. So because you're dividing, you take the reciprocal of your denominator, and that becomes 1 over 5x minus 4 raised to the power of 3 over 2. So when you simplify this whole term, it becomes 15x squared minus 16x divided by 2 times 5x minus 4 raised to the power of 3 over 2. And that's it. So this is your first derivative of y with respect to x. So this is not implicit differentiation. This is just all about applying the quotient rule and expressing your derivative in the form of x. And then for part C, that will be for next class, because it's going to take us a while for us to equate this being equal to your dy over dx for your implicit differentiation format. Okay, great. So yeah, thank you so much, guys, for tuning in, for attending my class. If you do found this helpful, I do have my daily schedule here, so it's oneclass.com/livestream. So this is where you can see my daily schedule. And also, there are other talented educators who are teaching on this platform, right? It's not just limited to math. We also do chemistry. So if you're interested, if you know anyone, your friends, your neighbors who can join, please feel free to ask them to check out this website, oneclass.com/livestream. And yeah, happy Monday. Thank you so much, guys, once again. I'll see you on my next class. Bye, guys.